So Relu, as you know, we have discussed it many times. It's so you can call it Mi as the output and Ni as the input, and as long as it is positive, it is the copy of that, and if it is negative, then it's 0. Yeah. So Mi is either Ni or 0. So this is the forward prop, simple. Now for backward prop, we know that we get the gradients from the the next layer coming in. The size of the gradient is the same as that of your output of M, which is the dimension of M, but it is a row vector, just that it's a row vector. And what we need is this Jacobian matrix. And what is this Jacobian matrix? It is the partial derivatives of the output with respect to input arranged in a matrix. And what is each of these partial derivative looking like? It's essentially saying, okay, I will differentiate the input with respect to input, right? I'll differentiate the output with respect to input, but the output is input as long as it is positive. If it is negative, it is 0. So there can be only two cases, right? So it will be either max of 0 comma ni. So there are only two cases. It's derivative of ni over ni when ni is positive. So when ni is positive, or it's the of 0, right? So we're differentiating 0 with ni where when ni is negative. So what is the answer in this case? This is equal to 1 and this is equal to 0. And this is, so let us just write this down. Let's say your M1 is equal to ni, if ni is greater than 0, and so let's just write it like this, right? So M1 is N1 or 0, M2 is N2 or 0, and M3 is N3 or 0. And let's assume it's a 3-dimensional input and the output is the same size as input. So now what will our Jacobian matrix look like? We know that we first write the output. So of M1 over N1, M1 over N2, and M1 over N3. Similarly, M2 and then finally M3. So this will go on the same, and then M3 over N1 dot 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 M3 over N3. Yes. And this is what our Jacobian matrix is. And now let us calculate each of these elements. So we saw M1 over N1 just here, right? So this is equal to either 1 or 0. So let me now rewrite it. So my first element will be either 1 or 0. What about M1 upon N2? Yeah, partial derivative by M1 upon N2. So your M1 does not depend on N, so your M2 depends on N2, but your M1 does not depend on N2, right? So this will be 0. Similarly, M1 upon N3, 0. Likewise, M2 upon N1, 0. Now it is only your diagonal element, so your M2 upon N2 can be 0 or 1, and here 0, and then finally 0, 0, 1. So your Jacobian matrix will essentially be an identity matrix if everything is positive, or it will be, so it will be all zeros except for your diagonal, and your diagonal can also have zeros, right? It will either have ones if your output was if your input was positive and thus your output was positive. Output is always 0 or more because we are gating it, but your input, so it can either be, so your matrix may look something like 1 0 0 0 1 0 0 0 1. It will look like this if all your inputs were positive, but let's say your second input was negative, so your Jacobian matrix will look like this. And if you multiply it, right, so and then we multiply it with the gradient that is coming in from here, so what we do is we are essentially doing a gating, meaning what we are saying is, let's say we have these 3 gradients coming in, right, because the size of the gradients is the same as the size of output, but when we had our inputs, this buddy, the second one here, was negative. So what actually happens because of the Jacobian is it kills this one. It only lets these two pass, right? Here it passes 0. So it acts as a gating mechanism to the gradients coming in. So an interview question anybody asks, so do you know what happens during a backprop of Relu? Yeah, I do, because what happens is if you have gradients coming in and some of your inputs were negative, let's say the middle input was negative, you just kill this gradient, right? So you then only let these two pass, and here it becomes 0. So that's all that there is, and we have also done it mathematically. We did it using our Jacobian method, and it works. Jacobian gives us identity matrix in the best case, or some elements of the diagonal of the identity matrix missing. When we multiply a vector with the identity matrix, we get the same vector back. So we get the same vector if the identity matrix was full, if all inputs were positive, otherwise we only get some of them, and so on. Yeah, and you can then also do it using torch. Like you see, I have created some input, and in my input some of them are negative. When I forward prop, all those that were negative become 0. And in backward prop, it's very simple and similar, right? So now whatever was my backward, it acts as gating. It only lets these two pass. Yeah, because I am saying that whatever, so I am getting all ones from here. This is my next grad, and I have defined it to be ones. But then when I pass it through my Relu, I only get 1 for 2, and the remaining I get 0, because it killed it, it made it 0. And now this is something that I want you to understand, because this is, in my opinion, an easy explanation of how activation functions help us, how activation functions can give us this non-linearities, right? Otherwise, why is everything linear? So let's look at why is everything linear. If, let's say, we start with a very simple neural network, and in our neural network we have x as input, and we have single weights here, right? So this weight is -2, and this has a bias of 8 and -8, and then here we have a weight of 3 and bias of 12. So then what is the value of this neuron? The value of this neuron is -2x -8, and the value of this neuron is 3x plus 12. And then we have our final output here, and we are saying, okay, I have weights equal to 1 and bias equal to 0, meaning I will just copy this over here. So the value of my final y would be -2x -8, and then it will just plus, because my weights and biases, weight is 1 and bias is 0, so it will be into 1 plus 0, and then plus again 3x plus 12 again into 1 plus 0. So this essentially becomes what? So now what I want to do is I want to plot these lines, right? So my -2x -8 is this blue one, right? So this -2x -8 is my blue line. And then my 3x plus 12, so 3x plus 12 is this red line, right? Now if I don't have a non-linearity, look what happens. It just becomes -2x plus 3x is x, and then -8x and plus 12 is 4. So it just becomes this x plus 4. So my final y in this case here became x plus 4, and this is my yellow line, right? So it just became another linear function. It just became another line. We don't want that. We want it to be more complex. So how can we do that? By putting a Relu. Now when we put a Relu, what are we doing? We are saying, okay, only when my line is positive, right? Only when my line is in the positive region, you give me the positive part. So it doesn't become this yellow line, instead it becomes this. Why? Because as long as it is positive, it says, okay, I'll take that part of your line. But when it is negative, it doesn't take it. It takes whatever is positive in the other one. Yeah. So this is why Relu creates this non-linearity. So if you were to write it down, what would you do? You would say your y now is what? Because we have a non-linearity here, so we will say we have a max of 0, minus 2x minus 8. Yes, and then because this is just this, we can then say, okay, then this is plus your max of 0, 3x plus 12. It means now we are saying we are taking the positive parts of both these lines. So we know, because we have plotted it, because this is one of our lines, right? This is our 3x plus 12 line, and remember the blue one is my minus 2x minus 8 line. So whenever this line is in the positive region, which is this region, I will take this, right? But as soon as it goes negative here, I will not take it. But at the same time, because it intersects, because I've made it especially like that, this line is positive here in this region. So I will take this region. And then this becomes my decision boundary, right? So I can use this to make a more complicated function. And if I have this complicated function, I'm able to separate my blue and green dots, which I was not able to properly here, because some of those green dots were being classified as red, because I could not create this nice complicated, function. But with the help of Relu, even with these two simple lines, I am able to create this complicated function. Instead of just one, I am able to create, like, this function that we just defined. And this is why we need nonlinearities. Again, so here I want to talk about another last concept for this video, which is vanishing and exploding gradients. So why do we need Relu? Right? We need Relu because we have all these gradients coming in, right? And it keeps getting multiplied. So even when we go 2 layers deep, when we want to update the values of W3, we see that we have gradients from here, and then all these Jacobians which then create gradients, right? So we have again this dou L by dou O into A. So up till here is then another gradient, and then this whole thing is another gradient, right? So we see, if we were not to use Relu and we were to use, let's say, a sigmoid function, right? So we know what will happen. In this region it is flat, so some of them will get killed. Yeah. So what will happen is you'll have this vanishing gradient problem, or if you have something like very large, it keeps getting multiplied, right? And when you multiply things repeatedly, it becomes larger and larger. So you get the so-called exploding gradient problem. And this is more apparent when we talk about, let's say, RNNs, recurrent models, and then transformers. So how did RNNs become better with transformers? We'll talk about that. But here what I want you to remember is your vanishing and exploding gradient problems. So because of this chain rule, because there are so many gradients getting multiplied to each other, if those were more than one, they quickly blow up. If they were less than one, or if some of them were getting saturated, they become almost zero by the time we come here. And this is the reason why earlier we could not have really deep networks, because by the time you came to the first layer, the gradients were zero, and then you couldn't update the weights of that layer because of this vanishing gradient problem. Yep. And this is why these nicer activation functions like Relu help us mitigate this problem of vanishing and exploding gradients.